Module 4, Part 2 covers adding, subtracting, multiplying, and composing polynomials and functions. So please make sure you're completing your guided notes as you go along. So a polynomial function of degree n is a term or a finite sum of terms, finite just meaning countable, right? I could count them, with only positive or zero exponents. So no negative exponents, i.e. no negative exponents. Or exponents that are fractions. That's something we won't deal with in this class, but that can happen. So they take on the form this, f of x, so equals a coefficient times our x raised to some power. So an example could be f of x is 2x squared plus 5x minus 7, right? And as long as they follow these rules, it's going to be a function, right? It's going to pass that vertical line test. Each x will have a unique y. When I'm naming polynomials, I can look at their degree, and I could say, oh, this is a degree 2 polynomial or a degree 5 polynomial. So we would say that the degree of an to the x is n, and the degree of a non-zero constant term is 0. So like we could say 7's like x to the 0 because x to the 0 is 1, right? And the constant has no degree, right? A constant has no defined degree. Constant 0 has no defined degree. And when we're choosing the degree of a polynomial, what we do is we pick the largest degree. So for example, if I have the polynomial f of x equals 5x cubed plus x, well, that x cubed is degree 3, that x1 is degree 1, but the degree of this whole polynomial would be degree 3. It's its largest degree. If I have the degree of f of x equals 5, that's going to be 0, because it's like I have an x to the 0. Remember, this graph looks like a horizontal line. The degree of f of x equals negative 2x plus 1 is 1, because it's like there's an imaginary 1 hanging out on that term, on that variable. And degree 1 polynomials we've looked at before, all of these are linear functions, right? This one has negative slope, but it could also have positive slope, right? And still be a function. Polynomials are made, can be counted or named specially by the number of terms that they have. Remember that the terms are the pieces that are added together or subtracted together. So a monomial, mono, meaning one, has one term. A binomial, like bicycle, or we as humans are bipedal, we walk on 2 feet, would have 2. And a trinomial, like a tricycle or a tripod for a camera, has 3. 1, 2, 3. And when I'm working with these polynomial functions, what I can do is perform our operations on them, like multiplication, subtraction, and addition, and they'll still be functions, right? So when I have 2 polynomial functions, what I can do is I can add them or subtract them by combining like terms. So let's take a look at a couple examples of what that might look like. So I want to find f plus g of x when f of x is 2x cubed minus 6x squared minus 3x plus 7, and g of x is defined by negative 8x cubed plus 4x minus 12. So I'm going to take f plus g of x. That means I'm going to take f of x plus g of x. Well, f of x is 2x cubed minus 6x squared minus 3x plus 7. I'm going to add that to negative 8x cubed plus 4x minus 12. Since I'm adding this together, I can kind of drop these parentheses by rewriting this as 2x cubed minus 6x squared minus 3x plus 7 minus 8x cubed plus 4x minus 12. Now I can combine like terms. What I like to do is I like to keep track of the terms I'm adding by underlining them. So I have a 2x cubed minus 8x cubed. That gives me negative 6x cubed. I have negative 6x squared. That's my only x squared term. So I have negative 6x squared. I have negative 3x and 4x. Negative 3 plus 4 gives me a positive x. And then I have just 7 minus 12. That's going to give me a negative 5. So f plus g of x would be defined by this polynomial that we found. I could also take a look at f minus g of x, which is our next example. So what I'm asking now is to find the difference between f of x and g of x. And when I'm subtracting, I need to remember that I'm going to have to distribute this negative. So I've got 2x cubed minus 6x squared minus 3x plus 7 minus negative 8x cubed plus 4x minus 12. I'm subtracting the whole thing, so I have to distribute this negative right here. So I've got 2x cubed minus 6x squared minus 3x plus 7 minus a negative 8x cubed, that becomes a positive 8x cubed, minus 4x cubed, nope, just x, not cubed, plus 12x, just 12. Why am I adding variables? Plus 12. Okay, so now we could combine like terms. I've got 2x cubed plus 8x cubed. That gives me 10x cubed. I have negative 6x squared as my only x squared term. I now have negative 3x minus 4x. That becomes a negative 7x. And I have 7 plus 12. That becomes a positive 19. So the difference of these two functions would be defined by this polynomial. Combining like terms is something you've done before since chapter 1, so it shouldn't be too new of a concept for us. Just using it with function notation might feel a little funky for the first few examples. So let's look at f of x equals x squared plus 1 and g of x equals 3x plus 5. I want to find f plus g of x. I could rewrite this as f of x plus g of x. And I can find this by taking x squared plus 1 plus 3x plus 5. So I combine like terms to get x squared plus 3x plus 6. But what if I wanted to find f plus g of 2? That 2 tells me that I am substituting 2 in for x. I could rewrite this as f of 2 plus g of 2. So I'm going to take 2 squared plus 1, because that's f of 2, plus 3 times 2 plus 5. In order to solve this, I'm going to follow my PEMDAS rules and add my constants together. So I'm going to have 4 plus 1 plus 6 plus 5. 4 plus 1 is 5, plus 6 is 11, plus 5 is 16. So that's one way to find this. The other way would have been, so here's another way, our second way. Since we knew what f plus g of x was, I could have substituted in 2 to this function. I could have taken 2 squared plus 3 times 2 plus 6. Well, that would give me 4 plus 6 plus 6, which would also have given us a 16, right? But it might not always be the case that I know what f plus g of x is, and then am asked to find f plus g of 2, right? So both ways would work. You kind of get to choose your favorite. The other thing we can do when we've got two polynomial functions is we can multiply them. So if I have fg of x, what that is saying is f times g of x. And there's multiple ways for us to write this. So let's solve some examples and practice. So if I want to find f times g of x, and f of x is 2x, and g of x is 4x, I could say f times g of x is f of x times g of x, and you don't have to rewrite it like this all the time, but that would be 2x times 4x squared. And now we can use our exponent rules to see I've got 2 times 4, which is 8, and x times x squared, which is an x cubed. Example 2 is going to use quite a bit more of our exponent rules. If I've got f times g of x, and f of x is 2x cubed over y, and g of x is x to the negative fifth over 8y to the fourth, I could have f times g of x is 2x cubed over y times x to the negative fifth over 8y to the fourth. That gives me 2x to the negative 2, because x cubed times x to the negative 5 is to the negative second, over 8y to the fifth, because this has a 1. And then I can simplify my fraction and move my x to the denominator. So this would give me 1 over 4x squared y to the fifth. For example 3, I'm going to have 3x squared y cubed, and g of x is 4x to the fifth y squared. I can multiply these together. I could even write it like this if I wanted, as fg, as opposed to f times g. That's going to be 3x squared y cubed times 4x to the fifth y squared. 3 and 4 is 12. X squared and x to the fifth is x to the seventh. Y cubed and y squared is y to the fifth. Now let's just take a look at multiplying some polynomials together. We're going to multiply monomials by polynomials, so monomial being one term. If I have 2x times x plus 4 I need to distribute, that gives me 2x squared plus 8x. For my second example, I have negative 5x cubed y times 2xy plus 4y to the sixth. So I'm going to pull this apart. I've got negative 5x cubed y times 2xy plus negative 5x cubed y times 4y to the sixth. And I broke it apart because I can do that in case we were forgetting our distribution rule. Defining variables, it looks like this, but this will make it easier for me to simplify. So if I have negative 5 times 2, that's negative 10. X cubed times x is x to the fourth. Y times y gives me y squared. Now I have negative 5 times 4, that's a negative 20. X cubed, that's my only x. Y times y to the sixth is y to the seventh. So we can't forget our exponent rules. We also can't forget our distributive rules. In example 3, I have negative 10x to the sixth times 6x to the 10th. 10 and 6 gives me negative 60. X to the sixth times x to the 10th gives me x to the sixth plus 10. That's our exponent rule. So negative 60x to the 16th. For problem 4, I have 7 times 5. That's 35. X squared and x cubed gives me x to the 2 plus 3, which is x to the fifth. Y times y squared gives me y to the first plus 2, so y cubed. My fourth example, I don't have a variable term that I'm distributing, just a negative 2. That's kind of nice. So I've got negative 10y squared plus 6y to the fifth, and these are not like terms, so I can't combine them. Last example, I have 4x squared times 5x cubed. That gives me 20x to the fifth. I have 4x squared times negative 6x. 4 times negative 6, that's a negative 24. X squared and x gives me an x cubed. And then I have 4x squared times 7. That gives me a positive 28x squared. And none of these are like terms, so I can't simplify this further. So our previous example was all about multiplying a polynomial by a monomial, something with one term. But what if I'm multiplying a binomial by a binomial? Well, for that, we use FOIL, which stands for first, outer, inner, last. And it's a way to make sure that every term is multiplied by all the terms it needs to be multiplied by. So if I was to have x minus 2 times 2x plus 6, I would run a FOIL. So I know that this means I need my entire second polynomial multiplied by x and my entire second polynomial multiplied by negative 2. So I first take x times 2x and then x times 6. Then I move to my constant. I have negative 2 times a negative times 2x. That gives me a negative 4x. And then I have negative 2 times 6. That's a negative 12. I can now combine like terms. You are going to need to combine terms most of the time. So I've got 2x squared, 6x minus 4x. That's a positive 2x minus 12. So that's how I would multiply those two binomials. And we are going to do quite a few examples. So here I've got x plus 3 times x plus 2. I'm going to have to FOIL. So I go first, x times x is x squared. Outer, x times 2 is 2x. Inner, 3 times x is 3x. Last, 3 times 2 is 6. And I like to use these lines to help me keep track of what I've multiplied together. I then combine like terms, x squared plus 5x plus 6. In example 2, I have negative 3x plus 7 times 2x minus 4. So I have negative 3x times 2x, so negative 6x squared. Negative 3x times negative 4, so a positive 12x. 7 times 2x, which is a 14x. And 7 times negative 4, which is a negative 28. I then combine like terms. Negative 6x squared plus 26x minus 28 is my final answer. For problem 3, I want us to treat these very carefully. It's 4x minus 3 squared. What that is saying is I want 4x minus 3 times 4x minus 3. I can't distribute that exponent over subtraction. It doesn't work like that. So my first step is always to rewrite it as two binomials. I can then FOIL. 4x times 4x is 16x squared. 4x times a negative 3 is a negative 12x. Negative 3 times 4x is a negative 12x. Negative 3 times negative 3 is a positive 9. And then combine like terms. 16x squared minus 24x plus 9 is my final answer. For problem 4, I've got two binomials, but we might notice that they look a little similar, except the only difference is their sign. So I wonder what's going to happen here. I'm going to have x times x is x squared. X times 2 is a negative 2x. 2 times x is a positive 2x. And 2 times negative 2 becomes a negative 4. This is an example of a product of a sum and a difference. And we'll talk more about these when we come to factoring. But what we're going to notice is my middle terms, negative 2x plus 2x, those cancel out. And I'm only left with two terms. My middle term cancels out. We can multiply binomials by another binomial, but we could also use this same process for bigger polynomials. It just is an expansion of FOIL. So in this first example, I have 2x plus 1 times x squared plus 4x plus 5. So I need to make sure I take 2x times everything in this trinomial and then 1 times everything in our trinomial. So 2x times x gives me 2x cubed. 2x times 4 gives me 8x squared. 2x times 5 gives me 10x. Let me fix that. That wasn't my neatest x squared moment. Now I'm going to take 1 times x squared to just get at 1x squared, 1 times 4 to get 4x, and 1 times 5 to get 5. I now have 6 terms. That's a lot, but I can combine them. I've got 2x cubed. That's my only cube term. 8x squared and x squared give me a 9x squared. 10x and 4x give me 14x. And my constant is a 5. Last example of multiplying by a binomial is we are going to have x plus y times x squared minus xy plus y squared. And this is something really special is going to happen here that we'll see more of in chapter 5. So I'm going to take x times x squared, that gives me an x cubed, x times a negative xy, that gives me a negative x squared y, x times y squared, that gives me a positive xy squared. Now here's my quick note. Yes, you could have written y squared x, but in math, what we typically want to do is we want to put our variables in alphabetical order. It also helps me see that these two are indeed equivalent, and it'll make it easier for me to combine like terms. So when we're dealing with multiple variables, make sure they are alphabetical. Now I do my y times x squared becomes an x squared y. Y times a negative xy is a negative xy squared, and y times y squared becomes a positive y cubed. So I've got x cubed, I have negative x squared y and a positive x squared y. Those cancel out. I have xy squared and a negative xy squared. Those cancel out. I'm left with x cubed plus y cubed. This is a sum of cubes, and we're going to learn how to factor these in chapter 5. Our last example of multiplying functions before we take a look at composition is this example here. So I have f of x is 3x plus 4 and g of x is 2x squared plus x. So I want to find f times g of x. When I write them together like this means multiplication. So I want f of x times g of x. That's going to be 3x plus 4 times 2x squared plus x. So I FOIL. This is going to give me 6x cubed plus 3x squared plus 8x squared plus 4x. And I can combine like terms to have 6x cubed plus 11x squared plus 4x. Part B of this problem wants me to find f times g of negative 1. This means I'm substituting negative 1 in for x. I could, if I wanted to, substitute it into this equation. I could also solve it another way. I could find f of negative 1 times g of negative 1. Well, f of negative 1 would be 3 times negative 1 plus 4 multiplied by 2 times negative 1 squared plus a negative 1. So 3 times negative 1, that becomes a negative 3 plus 4, which is 1. 2 times negative 1 squared, negative 1 squared is a positive 1, that becomes 2, plus a negative 1, that's minus 1. So I get 1 times 1, which is just 1. The last concept we're going to cover in Module 4, Part 2 is function composition. So functions composition is if I have two functions, f and g, I can compose the two functions by substituting g of x in for x in f. We've solved systems of equations by substitution. This follows the exact same idea. So, first example, extra bonus example. If I have f of x is 2x, right? This is a linear equation with a slope of 2 and a y-intercept of 0. And g of x is negative 3x plus 4, and I want to find f composed with g of x, what I'm asking you to do is substitute g of x in for x in f. So instead of having f of x be 2x, it's going to be 2g of x. Well, g of x is negative 3x plus 4. So then I just distribute to get negative 6x plus 8. This would be f composed with g of x when f of x is 2x and g of x is a negative 3x plus 4. We are substituting g of x in for x in f. Let's do a couple of examples. So let f of x equal x squared and g of x equal x plus 3. So if I want to compose these two, I want to note real quick that this is an open dot. F closed dot g of x, this is multiplication. This open dot, this tells us we want composition. So I like to rewrite this as f of g of x, because this kind of tells me, okay, I'm substituting g of x in for x in f. So now, instead of having f of x, I'm going to have f of x plus 3. Well, f of x is x squared, so now I have x plus 3 squared, which I need to rewrite as two binomials. And then I can FOIL to get x squared plus 3x plus 9, or x squared plus 6x plus 9. If I want to find f composed with g of 2, I could substitute it in to f composed with g, or I could take f of g of 2. Well, f of g of 2 would be 2 plus 3, because g of x is x plus 3, so I take 2 plus 3. So now I need to find f of 5. Well, f of 5 would be 5 squared, which is 25. And we'd get the same answer if we'd plugged or substituted 2 into this, because I'd have 2 squared plus 6 times 2 plus 9, 4 plus 12 plus 9. That gives me 25. We would have gotten the exact same answer. Our last example, let's let f of x equal 4x minus 1 and g of x equal x squared plus 5. So I now want to find g composed with f of x. This means I'm substituting f of x in to g. So I would have g of 4x minus 1. Well, that is 4x minus 1 squared, because that's my x, plus 5. So I'd have to FOIL this out and add 5. I get 16x squared minus 4x plus 1 when I FOIL, plus 5. So my final answer would be 16x squared minus 8x plus 6 is g composed with f. I can still also substitute in a specific value for x. In this case, when x is negative 2, I take this as g of f of negative 2. So g of 4 times negative 2 minus 1. That's g of 4 times negative 2. Negative 2, that would be a positive negative 8 minus 1. So now I have g of negative 9. That means I want negative 9 squared plus 5. Well, negative 9 squared is 81. 81 plus 5 is 86 for our final answer.